Thank you, Patrick, for the introduction, and thank the organizers to bringing me here. And today I'm going to talk about my joint work with Frank Calegari and Vesselin Dimitrov, and Vesselin will give the second half of the talk. And so since I only have 30 minutes, and I decided to do a blackboard talk, so which means I'll skip some of the history about what are many previous people's work on this subject, and please feel free to ask me or Vesselin if you are interested in a more historical part of our work. Okay, so I'll get to our theorem and the mathematics behind it. Let me start from stating the theorem that's where I'm going to start my talk. And that's the theorem that we posted a paper on arXiv last year, that we proved two irrationality in the result. Namely, is if we consider the Dirichlet character with conduct -3, and we consider L value at 2, this is saying that we'll consider the sum of this number, and then we prove that this is irrational. And when you're looking at this result, I would recommend you to think about Apres theorem saying that zeta 3 is irrational. And our proof, the starting point, is from there. And the other theorem that we have is we talk about certain log values. So we have mn are integers. And then we consider the product of log values. And then we expect from Shanya's conjecture, we would expect that this number to be irrational. Sorry, this number to be transcendental. And then we prove this number is irrational under the condition that the ratio of mn is very close to 1. Okay, so one of the goals of today is to explain to you where this condition comes from in our method. So we have two irrationality results. And then the first thing that I want to emphasize today at this conference about Diophantine approximations is that we actually have a effective version. So let me make it more precisely. And Vesselin will talk more about this in his talk. Okay, so I'm going to talk about the most naive way of talking about irrationality measure is that, let me write down the statement, is, so assume there exists an infinite sequence of rational numbers Pn over Qn, so Pn and Qn are integers. Such that, so for, I'm going to talk about a real number because these two examples are both real numbers. Okay, so I use the familiar notation kappa means it's we're going to give an upper bound of the number kappa here, and hence you can view it as an upper bound for the irrationality measure when you consider how close a rational number to an irrational number with respect to powers of denominators. Okay, so the bound that we get is the following. I'm going ahead of myself. So there's some data. So it's some phi and sigma, which will depend on the generating function. So this is related to the word power series in the title. So depends on the generating function of the rational approximations used in the proof of the theorem that I'm going to tell you in a minute. So I'm just saying it's there will be two data. And what are these two data? at this moment, it's just to set up the definition. So phi will be a map from the closed unit disk to C such that phi 0 equals to 0, and the derivative is not 0. Okay, so basically this gives you the information of the Archimedean convergence property of the generating series, and a sigma is a positive integer, which essentially speaking, I'll make everything precise in a minute, which controls the denominator of your generating series. Okay, so with these two data, what we have is the following. So let me go to the blackboard. So we have I'll introduce another notation, which I'm going to explain in a minute. So two more things, and then what is rho? So rho is going to be a positive real number, which records the absolute value of the first singularity of the linear ordinary differential equation satisfied by the generating series. Okay, and m is equals to the dimension over qx of all possible functions with similar Archimedean and non-Archimedean property as the generating series. Okay, so here things are a little bit vague, but let me just tell you like what is the motivation which give a hint towards the proof is that so from rational approximations to the values that we are going to prove irrationality, we'll get some natural generating functions. They are actually solutions of some linear ODEs. Yes.
Because I cannot see m.
Oh, sorry. Is this okay?
So go down the system.
Oh, I see the point. Oh, sorry. Let me just read that to you. Okay. So. Sorry? Do you want the board to be up or down? Oh, sorry. Okay. Okay. So let me talk a little bit before I go into the detail. Let me talk about what is the philosophy behind it. Is that so you're starting from proving, so the proof of our theorem is based on classical rational approximations considering the literature. I'll give you a detailed explanation about what happens in the log case. So you have some general generating functions coming from the rational approximations. And then so from that generating function, you're going to choose a nice phi, and you're going to observe the sigma, which actually gives you the Archimedean and the non-Archimedean property of your generating series. And then so it also gives you the rho, which coming from the ODEs of this power series. And then M would be the space of the dimension of the space of all functions with the property. And then our proof of the irrationality measure, our proof of the theorem, what coming from is like you draw a contradiction from this inequality. And once you have a contradiction, namely it's like you have m is greater than these parts without the irrationality measure input. And hence it will give you an upper bound of the irrationality measure. So we'll see a concrete example of the log theorem so that everything that I said abstract here will make more sense. But the upshot I want to mention is that, so today I'm going to talk about the irrationality proof, and then the upshot is like you can actually upgrade everything into an effective version, which gives you an upper bound of irrationality measure. And more precisely, it's like the proof is actually effective. What you'll see in Vesselin's talk is that, so here I write this as smaller than equals to with an inexplicit constant, but you can actually make that constant also explicit. Okay, so that's the idea about our work, and now I'm going to make things concrete. So I'm going to explain the vague words that I talk about. So the first thing is like, I'm going to give you a sketch of proof for this one log value is irrational without using Baker's theorem. Okay. So the first thing I'm going to tell you is like, instead of telling you what are the rational approximations and how to get a generating series out of it, I'll just give you the generating series on the nose, and along with the linear differential equations. Okay, so for the ease of notation, let me just set A to denote, why is this one? 2m plus 1, and for simplicity, we may assume that m is at least 1, because it's like you can use the log rules to switch between like positive and negative numbers. And then we're going to consider, so the A and the H here will be the generating series that we're interested in. Be solutions to the following linear ODE. So y is the unknown, and x is the coordinate. So x is coordinate on A1. Okay. And then, so A corresponding to the one such that it satisfies this first order differential equation, and then H is the one such that it goes to 1. And then to pin down these two things, I'll set A0 to be 1, and H0 to be 0. Okay, so here I write down for you the explicit differential equation, but the differential equation doesn't matter for us. As you see, it's like what's important, especially when you think about like the information that we have here, is we only focus on the singularities. So the key point is like the singularities are a plus minus a squared minus 1. So this is the important part that we are going to remember. Okay. And then so why is this, like I say, the generating series of the rational approximation, so the log should show up somewhere, is that we actually have, so the important property is that we have hx minus a half log 1 plus 1 over n times ax is actually well defined, so it doesn't have singularity, so well defined at a minus the smaller singularity. So you can do this by checking the local monodromy of it. And the second part is we do have that 1 over n, this denotes the LCM of these numbers, kills the denominator of the nth coefficient of ax and hx. Okay, so actually, ax has integer coefficients, but like that doesn't matter for us right now. So let me just say it's like we do have the control of the denominator of these two functions. So that's what we mean by like you can think about the first thing as some like Archimedean properties, and this is a non-Archimedean property. Okay, so why is this good for us? Let me just tell you what people think about differential equations. So actually, it's like when we have, so here is like you can say that we have like a differential equation defined over a number field, and then what do we know about differential equations defined over a number field? So there's a conjecture goes back to like Grothendieck and Katz, which gives you a local to global principle of like differential equations over a number field. And then let me not jump into about what it is. It's a local to global principle, and let you to imagine what's the precise formulation. What I want to say is like when people try to study that conjecture and then actually prove some special cases of the Grothendieck-Katz conjecture, it goes back to the work of Chalonsky's, and then it is actually refined and reformulated in Evangé's work. And then, so let me just set up the data of phi and sigma and tell you what Evangé's work said in this case, is that we consider all the power series such that it has, so now I'm going to explain it's like similar Archimedean and non-Archimedean property. So such that is like 1 to n to the power of sigma ain are integers. Okay, so for this case, it's like if I'm going to take the generating series, so sigma will be 1 in the above case. And the second part is that, so the pullback using phi of these functions fi are meromorphic on the unit disk. Okay, so the first thing I said control the non-Archimedean part of the coefficients, and why is the second thing control the Archimedean part is like if I just choose my phi to be a scaling map, which scales like the closed unit disk to the radius of convergence, and then this information, so like the phi actually capitalizes the information of like convergence radius of the power series, and then which actually the first property up there just tells you that indeed the convergence radius of this particular power series h minus log times a actually has convergence radius to be the larger singularity. So that's why like you capture the information about the rational approximation. And one thing I forgot to say here is that, so I said these are generating series of the rational approximation. Where is the rational approximation? The rational approximation is actually you have the ratio of the coefficients of h over the coefficients of a, that gives you that limit which goes to the log value. Okay, and then that is capitalized in this property, and then you can actually remember both properties in terms of the sigma and the phi here. Okay, so what Evangé proved is the following, is like if, so I'll state this as a proposition, if, so the log of the derivative is greater than sigma, then, okay, let me just say they are linearly independent over Qx that matches with like what I said about M and the dimension. Then M is smaller than equals to some explicit bound in terms of phi and sigma. Okay, so that was enough to like get the Grothendieck conjecture, knowing that you have a finite bound. That is enough for the purpose. But like for later applications in our work, you would actually want to have a explicit sharp enough bound. And let me just mention is like the first case that when we try to work for a like good bound rather than there exists a bound is like in our earlier work with Calegari and Dimitrov on like unbounded denominator conjecture. And that was the case when we have like sigma equals to 0. So back then we improved André's bound and proved the unbounded denominators conjecture. And after our paper was posted, then Bost and Shah try to give a more geometric interpretation of the bound that we are working on. So let me just state their theorem. And then, yes?
You have two different m's on the board.
It's the same m.
It is the same
It is the same m. That's why I put the linear independent condition here.
This dimension that you
Yes. Yes, thank you for the question. Yeah, I intentionally use the same thing. It's just like, so here is like, you don't need to find all of them if you don't know all of them, but you just try to find as many as you can for the functions of this property. Yes. And this is the true properties are what I mean by the Archimedean and the non-Archimedean properties. Let me go back. Thank you for the question. Yes, that's the m. So I'm saying it's like m is the dimension of all the possible functions satisfy the similar Archimedean and non-Archimedean property as the generating series. And then so here I'm saying it's like this is the non-Archimedean property. That is the Archimedean property. Oh, sorry, that's not the same m. Oh, yeah, that's a different m, sorry. Oh, thank you. Okay, so, and what they prove is the following, is that the dimension bound is smaller than what I wrote. I should have just the double integral. And then let me just say, in the case of phi is the scaling map, and then the dimension bound. So the dimension bound is equals to 1. Okay. So let me go back to like what happens in the proof of the log results and what we're using here is like, so I said the dimension bound equals to 1. Namely is like you would have, so let me actually go back to this case, is like indeed we have log of a plus a squared minus 1 is greater than 1. So this is the derivative of phi, and this is our sigma. So and hence it's like you apply, of course, like this result is known way before that. It's a classical thing. Then you apply the result that dimension bound saying is like if, so log case, if f define, if the log value is rational, then we have this f defined to be h minus a half log a is qx coefficients. And then the dimension bound implies that f lies in qx. And this gives you the contradiction because you can, I mean, the function f is very concrete. You can verify it is not like a rational function, and hence you got a contradiction. Okay, and then what do we do is the following. It's like in our case, so for theorem, part 2, is that you can actually using, so let me denote h1, a1 to be the one for like log 1 over n. Sorry, I recycled my m again. And the h2, a2 for log 1 plus 1 over n. And hence we can take the adma product, so h1 adma product h2 minus 1 over 4, the log values, actually has satisfy a linear ODE with singularities in disks D. Okay, so basically when you take the ultimate product and the singularities of the new differential equation will be 0, infinity, and the product of the singularities. And our condition that the ratio of Mn is very close to 1 means the singularities of the two differential equations for like H1A1 and H2A2 are very close. That's why when you take the product, it's like you have some singularity close to 0, some singularities close to 1, and some singularities very close to infinity. And that's all the information you need to remember. Okay, and then so we're going to apply our dimension bound. So let me just mention that in our work, we have a slightly improvement of the dimension bound, is that we have this minus some, we call it convexity improvement from some further complex analysis. And then we can also improve the denominator to get a better bound. And then what we have is, so we apply our dimension bound to, okay, what is the phi? So the key question is like, so we have sigma equals to 2, because when you take the product of power series, you're bound for the denominators just to take the product. And then we apply the dimension bound to phi, which here I'm going to say approximately equals to the lambda function. So lambda function is like you have the up half plane goes to c minus 0, 1, which is give you the isomorphism between like H2 modulo of gamma 2 with like c minus 0, 1 infinity. And then you can actually consider the Q expansion. So this is actually Q maps to gamma Q, sorry, lambda Q. You can have the Q expansion, which is D goes to c minus 1. And then you're going to take phi to be approximately this function, and then I'll leave it as an exercise to see is like why, due to some simple topological and complex analysis property, you would have the pullback using phi of this function to actually be convergent. And then the upshot is like the log of lambda at 0 is log 16, which is greater than 2. And then we apply dimension bound to these two cases. We have a dimension bound to be at both 9, and then we find 9 functions. Okay, so to make it a little bit more concrete, it's like, so we're going to apply the theorem with f1 equals to 1, f2 equals to the log function, f3 is Li2, f4 is log square, and f5 is the following iterated integral. And f6 is the above generating series. And f7, because it actually satisfies a differential equation, so you can have f7 to be the derivative of f6, and f8 to be this following change of variable, because this change of variable keeps 0 to be 0 and swap 1 and infinity, and then you have f9 to be the derivative of f8. So, okay, so let's go back to the beginning setting. It's like we find out the phi and the sigma with respect to the non-Archimedean Archimedean property of the generating series. So then you get phi and the sigma. And once you have finite sigma, you try to find all the functions, because the more functions you find, that the larger m that you put here, which will give better information of the bound. And you try to find all the functions with the property. In this case, we find 9 functions. These are honest functions in Qx. These are the things which shouldn't exist if we do not assume, so this will be assumed for contradiction. The log value is rational. Okay, so, and then you have like 4 more functions if you assume this log value is rational. Okay, then our dimension bound says that you have like less than 9 functions. So, which means it's like, here's a contradiction. You shouldn't have 9 functions. Where does the contradiction coming from? It's coming from that this number shouldn't be rational. Okay, and then so back to there is like you will have a dimension bound in general about like the dimension m will be larger than the right-hand side without the contribution from the irrationality measure. And hence, whenever you can prove irrationality using our method, you can always like get an upper bound of kappa. And then that'll give you an upper bound of kappa. And because the whole proof is like quite explicit, you see some idea of proof in Vesselin's talk is that you can actually also make this like implicit constant explicit. So like the whole method is quite like effective, and I'll just stop my talk here. Thank you.
All right, thank you, Yunqing. Do we have any questions for the speaker?
Thank you for the nice talk. And my question is about the irrationality measure. By your method, is it possible to improve, for example, irrationality measure of log 2?
So we do not, oh, that's a good question. We do not, so far, not yet. Okay, by so far not yet is a safe answer. Is that, so if we apply the method to the case that about like phi is the scaling map, and then you are in the classical range, and then unfortunately this 2 here is the part that we're off from the classical method. If I put a 1 here, then we would recover the classical bound. And then we are working towards improvement about how we kind of combine our method and the classical method, at least to like recover the classical case, and then we have hope to improve the classical measures.
Thank you.
Wait, was it? Oh. Michelle.
Thank you. So this is a very nice result. Congratulations. And my question will be, what about the product of 3 logs?
Yeah, that is a little bit tricky. So I can tell you what we know is that, okay, so as I said, here is like, the first thing is like you want, okay, that is the first thing you definitely want to have, is the Archimedean contribution should be larger than the non-Archimedean contribution. And then here is like we have sigma equals to 2 when we have product of 2 logs. So you have sigma equal to 3 for 3 logs. 3 is greater than log 16, but that's not a nightmare in the sense we do have some improvement that we can make here. And then the issue is like, you also, like the 16 here coming from that you have like singularities to be close to 0, 1, infinity. That's the best possible case after you have the like monodromy group to be solvable case. So the first like non-solvable monodromy group. And then we are lucky in this case is like we do observe a condition such that you actually have the singularity to be 0, 1, infinity, roughly speaking. But we just don't have such a nice condition for the 3 logs. So, I mean, it's not impossible, but we just don't have a theorem. Yeah.
Is there another question at the back? Okay.
So in the proof of theorem 2, you had the upper bound of 9,
yes.
And you found 5 independent functions independently of your assumption.
Yes.
Would you expect that the dimension is actually 5?
Yes, but we don't have a proof yet. So yeah, that's a good question. I tell you what we know is that, so that's the great question that you asked is like, we have some leeway space. It's the same case in our unbounded denominator later conjecture proof is that we have some leeway to prove the theorem. We don't need to have the sharpest possible bound, and then we can still prove the theorem. And then you can ask it like, when is the bound sharp? And then the two cases we know is that for sigma equals to 1, we only have 1 and the log, and that we can prove it's sharp. And then, so the dimension bound is smaller than 3. And then for like sigma equals to 1/2, namely you have this one, and that one, that case will also prove it's sharp. So the next case would be sigma equals to 2, not yet. Yeah.
Great. Are there any other questions?
Thank you. So I have a question about the type of differential equation that you start with.
Yes.
If you play a little bit with the coefficients, which are functions in x,
Yes.
do you get some other interesting numbers, or do you expect to get some other interesting numbers?
I think if you play with, for this particular one, I expect you always get log.
You always get logs.
Yeah. But there are other differential equations to give you other values. For this one, I expect you get. Okay. Essentially, like things closely related to log.
All right, any other questions? If not, let's thank Yunqing again.
Thank you.